for small, by inspection of what happens for small n's. What is happening here? Yes, so you see quickly, if you look at U4, you can see where you're picking up one term in each polynomial for each partition of n. There are many presentations, or some of them I'll give later, as these polynomials as sums. You can write them as sums over permutations or partitions or compositions. And there's a long history of variations of these formulas. And I list some of the mathematicians that have been involved there. Okay, so just to put many familiar Taylor expansions in this framework, this is Stanley's notation for R multi-choose n. It's the number of for R a positive integer, it's the number of multisets of a set of R elements, multisets of size n. It's a rising factorial normalized by an n factorial. This is actually a binomial coefficient if R is a positive integer, and in general it's a -1 to the n times an ordinary binomial coefficient with the usual convention of sort of polynomial continuation of binomial coefficients. So this is sort of, you know, Newtonian or Pascalian mathematics. You have the basic exponential series, you have Newton's binomial expansion, you have Newton's binomial expansion with a negative index, and these are all three different instances of the general exponential expansion. So once you've understood that you can expand arbitrary powers, you realize that you're doing an exponential operation, and I've written it here in that way. I haven't written any conditions of convergence. Everybody knows that if we're dealing with real or complex numbers, we should assume that absolute x is less than 1 in these expansions. However, if you treat these as formal power series, there's no such restrictions. These formulas just work at the level of formal power series. There's no issue of convergence. The whole idea is that, you know, a function, what we think of as a function like x bar x, it's actually identified with the sequence r to the n over n factorial. And these are just the coefficient sequences are doing all the work. Okay, so let me give a kind of overview of the main probabilistic interpretations of this X-blog correspondence that I'm aware of. The first one I'm aware of that's explicitly in the literature is what most people would call the moment cumulant correspondence. This is due to Taylor explicitly in the 1890s. It has a longer history earlier than that, goes back to Laplace and Bien-Aimé and others who typically did a few terms but didn't try and write down the general thing. Once you're into moments and cumulants, you get into the world of normal Poisson infinitely divisible laws, and the exponential formula of probability is the Lévy-Khinchine formula. Then we have compound Poisson distributions as an instance of that. And now in a very different vein, we realize that the exponential formula in a combinatorial form is actually giving what Polyu would call the cycle index of a uniform random permutation, or it's the cycle index of the symmetric group in more algebraic language. We have a further interpretation in terms of renewal sequences, which is implicit in Feller's work in the 50s. And that really comes to fruit in the fluctuation theory of random walks and Lévy processes, which has, it's really progressed. It exploded in the 1950s with dozens of papers, and then developed further in the 70s, 80s. And it continues to be an active area. People are doing finer things with Lévy processes and so on. Key ideas around here are ladder indices, concave majorants, and various Poisson constructions, which I refer you to some work that I did with Josh Abramson, Nathan Ross, and Geronimo Uribe Bravo around 2010-11. We wrote a series of, I think, 4 papers with various aspects of Poisson constructions. So this, I'm coming back to this as a sort of, trying to get some wisdom of hindsight about what's making things work and increased respect for how much knowledge there is already in Euler 1755. Okay, so let me say quickly the moment-cumulant correspondence. If you have a random variable with moments mu_n, the cumulants kn are defined by the moment-generating function. We assume we have a convergent moment-generating function in the first instance. We write it down, and we prefer to see it as an exponential because nice things happen inside the exponential, as we know from the normal and Poisson case. So that's saying that the moment-cumulant correspondence between the moments and cumulants of a random variable, in the previous language, it is that the sequence of moments normalized by n factorial corresponds by the x log ratio transformation to the sequence of cumulants normalized by j-1 factorial. And there's some level of artifice or artifact in handling the factorials. To my mind, there's no good reason for putting j factorial rather than j, or rather than no coefficient in the definition of cumulants. Whatever definition you made, you'd have these some basic formulas, and they would be easily manipulable into others. So I just prefer to have a 1 over j inside the exponential. So when you recode like this, you realize that Euler's recursion for, if you take your un to be a mu_n over n factorial, and you take an rj to be a cumulant over j-1 factorial, you get what is known as Taylor's recursion from about 1890. And you can see what happens is that you have factorials pushed into the recursion, and they're most cutely arranged as binomial coefficients. This is, of course, an n factorial divide I factorial n minus I factorial. And that appears to be an I, not a J in the index. Now, this recursion is much harder to understand or interpret, and cumulants are not terribly intuitive things for general distributions of X, but nonetheless, you can use this formula effectively, and statisticians do it. Fisher, in particular, developed quite a lot of statistical theory around cumulants, and use something like this as a sort of a polynomial definition of cumulants in terms of moments. And just, I'm not going to say anything more except to say that this formalism of formal power series, it pushes to new directions in the last decades, notions of free cumulants and extensions of this exponential correspondence to random matrices and the like. I won't say any more than that, just to acknowledge that that universe is there. Okay, I want to say one or two things about the normal distribution. This goes pretty quickly because everybody knows the normal MGF. And so in the X log notation, this says that a sequence of B1 is a standard normal variable, Brownian motion at time 1. These moments of a Brownian motion at time 1, they correspond by the X log transformation to two numbers. You just need a mean, and you need a sigma squared, which has to be non-negative to make sense of the probabilistic interpretation. This has well-known combinatorial interpretations in terms of matchings, which I won't go into, but again, just to say that it's there. I want to pick up on one theme of this, which I've found interesting, which is we have a Gaussian variable if the moment generating function simply has two terms inside the exponential. And Kahan in 1960 came up with a very clever definition, which is to say that a random variable has a sub-Gaussian distribution if its moment generating function is dominated by the same expression that you get for the normal case. Now, it's easy to see that if that is the case, then there's only one choice for the mean. There's only one choice for the parameter mu. It's got to be the mean, which has to exist. And obviously, if you have this expression for some sigma, you have it for all bigger sigma. And arguably, there's a minimal sigma. And that's what Kahan called the sub-Gaussian standard. That's a rough English translation of the distribution of X. And so beware, sigma is the minimal thing that works in here for a given X, which may or may not be the standard deviation. And it's always at least the standard deviation due to this inequality, which is quite elementary. Now, things get more interesting when you look at tails. If you look at the right tail, the probability that X centered at its mean and normalized by its Gaussian standard is bigger than X. There's a very easy inequality, which goes back to Chebyshev and Cantelli, which is just really a second moment inequality, which says that this is bounded above by 1 over 1 plus X squared. And there's a much more clever inequality, which is due to Kahan in 1960, which would now be regarded as a large deviation bound. And it's an instance of Chernov's inequality. The proof is quite elementary. The proof is you just do the usual, you apply Markov's inequality to the inside to the exponential, and you optimize the result. And using the Gaussian form here, you find that the optimum result from that method is e to the minus x squared over 2, which is, of course, a terrific tail bound if you have this condition holding. Now, I've often wondered about the quality of these two bounds. They're very different. For small x, this guy is bigger. For large x, this guy is bigger. And it's very interesting to find what is the best bound. And I have a question to this audience, which is, has anybody seen this fact in the literature? The easy fact is that there is a least upper bound, and the more challenging thing is to find it and understand what it is. I claim that the least upper bound is given by this formula, and it makes a very surprising connection between the sub-Gaussian world and the Poisson world, because there's a fairly easy argument that says that this least upper bound, assuming it exists, it's got to be attained by a two-point distribution. And then it's what seems superficially an easy problem to do a maximization over two-point distributions. But the calculus is quite involved. When the smoke clears, you find that the function R of mu that's involved here is a very old friend to most probabilists. Namely, if the mu is bigger than 1, this function R of mu that appears here, it's actually the extinction probability of a Poisson-Galton-Watson branching process. And I have two questions for the audience. One is, did you know that this was the least upper bound? And two, can you give any reasonable explanation of why Poisson-Galton-Watson probabilities should appear in sub-Gaussian tails? I have nothing but a rather brutal calculus proof of this. Just to remind you of the Poisson extinction probability and related functions, the function R of mu, these are the roots of R is e to the mu R minus 1. If you multiply them by mu, you get a slightly more pleasant equation, which is you're looking at the two solutions. V e to the minus v is first increasing and then decreasing, has two solutions, and those solutions, so here is the Poisson, this is mu going horizontal, probability going vertical. The minimum of 1 and this R of mu is the Poisson branching extinction probability. When you multiply by mu, you multiply 1 by mu, there's the identity mu, and you multiply the other guy by mu, and you get this curve, which is it's symmetric across the diagonal. The symmetry is apparent in this formula. And that kind of involution is present in many branching process settings. So I just quickly show you what the bounds look like. So here is the top one. The highest one is the Kahan bound. It's too high at the beginning and much lower at the end. The blue one is the Cantelli bound. And the green one is what I claim is the best bound, which has a connection with Poisson distributions. And these are the absolute numbers between 0 and 1 here. And in the bottom panel, I show you the relative thing. So I'm using the green as a benchmark. I'm calling it 1. I'm looking at the others relative to it. Exactly at 1, there's a coincidence, which you see here. And what this shows is that the Kahan bound is awfully good. It is asymptotically correct, equal to the least upper bound. You cannot do better for large X. And even for small x, you're only off by a factor of about 1.2, which comes from a particular evaluation. Anyway, I just throw that in for interest and diversity in the talk, because otherwise it is a lot of polynomials and formal power series, but I'm interested to see if anybody is aware of this kind of calculation for sub-Gaussian distributions. Okay, so something completely different, and that's part of the point of my talk, is how varied the expressions of this X-blog business can be. Let's take a very generic model for a discrete distribution on non-negative integers. We take a power series A of X with non-negative coefficients, and we renormalize it to make a probability distribution. This is called a family of power series distributions. We have a parameter X, and the generating function is just given by a ratio of 2 evaluations of the power series. And if you can easily, in most circumstances, and I think in any generality, you can construct random variables like this in a way that is increasing. It's stochastically increasing, and hence increasing in various ways. And the simplest case to think about is if your basic power series already sums to 1, and then the y of x is your y of 1 conditioned on being smaller than a geometric variable. And g of x is denoting a geometric with parameter 1 minus x distribution with its tails are x to the k. So this method of introducing an independent geometric variable to interpret the power series is surprisingly powerful, and lots of things acquire interpretations that way. And a general comment, basically all the fundamental discrete distributions are constructed this way from some basic power series. So that ties in very nicely with renewal theory with Feller. If in fact, the whole UN notation is adopted from Feller's renewal theory. Feller has UN as the probability of a renewal at time n, and f of x is the renewal probability, the generating function. Its kth power is the generating function of the time of kth renewal. In this case, my power series is 1 plus ux. I just like to have ux starting with an x term, not a 0 term. And then my 1 plus ux, it is a 1 minus f of x inverse in the world of power series. So if we look at the last renewal before time n, then we can simply write down the distribution of the last renewal of time n. You've got to have a renewal, and then a renewal spacing has to be bigger than what's left. And if you sum that over k with an x to the k, you learn that the time of the last renewal up to a geometric independent time is going to have this power series distribution, and you can write the generating function like this, and you have the quite natural in Markovian settings interpretation that this last renewal before independent geometric killing, it's a compound geometric variable. It's a sum of IID copies of the basic inter-renewal thing, given that it's smaller than a geometric, and then the number of copies is just has another geometric distribution. So this is all very familiar to people in a Markovian setting. Now, the connection between renewals and exponentials gets a little trickier. In the setting of renewal theory, the most familiar recursion to most people is this one that says that the renewal probability is related in a recursive way to the first renewal probabilities, Fj. So this is a Feller-style renewal recursion. And just compare that with the Eulerian style recursion, which looks almost the same, except instead of summing, you're averaging. And of course, you have a different right-hand side. If you're thinking of, you can think of the UNs as driving the Fs, or here the UNs are driving the Rs. Both of these recursions are invertible. I think it's very instructive to think about them or compare, contrast them. So if you do that, you have the Feller-style renewal formula, and you have now the Euler-style formula for the logarithm. And if you compare those, you see that in the Eulerian recursion, the Rn over n, it is always the coefficient of x to the n in this expression. That was Euler's theorem. And this is like a corollary of Euler's theorem, which is that if you simply write your 1 plus ux as 1 minus f of x inverse, which is totally natural in the setting of renewal theory, then you can expand the log of this guy more pleasantly because all the coefficients are positive. You get rid of all these minus signs. And this is all working at the level of renewals with an arbitrary, even transient inter-arrival distribution. So the conclusion of that discussion is that the last renewal up to an independent geometric time is going to have a compound Poisson distribution, because we have the generating function. This is just basically copied from the last slide, and you inspect that generating function and you see the log of this generating function is the log of a ratio. That's a difference of logs. Expand each side, and suddenly you are looking at what any probabilists will recognize is the generating function of a compound Poisson, with the explicit representation that this last renewal up to an independent geometric time, it exactly has the distribution of a weighted sum of Poisson variables. You have the J is for basically jumps of size J. You have Nj. These are independent Poisson variables. These are their rates. And that's a very interesting and sort of, not obvious without the intervention of formal power series fact, which is you take any renewal process, the final renewal before an independent geometric stopping has a compound Poisson distribution, and you have it completely explicitly. You know what the parameters are, and you get the parameters out of that X-blog transformation thanks to Euler. So we are now very close to the Lévy-Khinchine representation of infinitely divisible distributions, discrete ones, and we have a sort of a wrinkle on that, which was described by Cati in the 1960s. And I'll just say it very quickly. You take any non-negative power series, and we're going beyond the renewal setting now, right? We're saying maybe it's renewal, maybe it's not, but take any non-negative power series, and then we know it's going to correspond to some Rn sequence by the X-blog transformation. And we can make these family of power series distributions. And then you have three equivalent conditions. One is that the Rn sequence that you get from the X-blog correspondence is all non-negative. One is that one of these distributions is infinitely divisible, and the second is that they're all infinitely divisible. and you have a completely explicit compound Poisson representation, and you get for free that as soon as the theta is such that the distribution exists, then this power series is going to converge. Anyway, this is discussed at some length in Stoitel and Van Haan's book, and not exactly in the way I present it, but if you reread their treatment, you'll realize that this can simply be read off from their discussion. Okay, so what has this got to do with fluctuation theory of random walks? Well, if you take a sum of IID variables and we say that n is a ladder index or an Li, if it's a weak increasing one, and we look at the cyclic shifts, then there is this brilliant idea which somehow emerged in the 1950s, thanks to Spar, Anderson, Spitzer, and others, but it's really crystallized by Feller, which is you take this random variable Kn, which is the count of how many different cyclic shifts make n a ladder index. And Feller's combinatorial fact, which is just a fact about real numbers, is that the event that Sn is non-negative is exactly the same as the event that this Kn is strictly positive. Kn is a discrete variable. It has values 0, 1, 2, up to n, and Sn is a real variable. And moreover, if there are k shifts which make n a ladder index, then n is the kth ladder index in each of the k shifts. So this is true for weak ascending. It's also true for strict ascending and descending indices also. So that enables you to write down that the probability that n is a kth ladder index, you basically do it by conditioning on this variable Kn. It is the probability that the final value is non-negative and you have k cyclic shifts. And then given that you have k cyclic shifts, essentially one of those is picked at random to be the real shift. And so there's this magic factor of k over n, which comes from the cyclic exchangeability argument. I'm not going to go into that in detail. This is a well-known argument. I'm just sketching it or trying to describe to you how the magic factors of the k over n come in. And you rearrange this identity and you see that 1 over k times the probability that n is the kth ladder index is 1 over n times the probability that Sn is non-negative, and this variable is k. And that is, n being a kth ladder index, this is a renewal thing. I mean, ladder indices are coming according to renewals. We have an f of x, which is the generating function of the first renewal. That's the first ladder index. And by this completely combinatorial argument, you arrive at this identity that the coefficient of x to the n in some logarithmically weighted renewal sequence of powers is exactly the probability that Sn is non-negative divided by n. Now, the consequence of that are really pretty stunning. They're basically due to Spar-Anderson, and they're developed in various ways by Baxter and Spitzer. But here they are. The consequence of that argument is that the probability that you have a run of n terms that are non-negative, I would call this a weak meander of length n. It is a universal polynomial function in the probabilities that you are positive. So this is a joint probability. These are marginal or individual probabilities. And there is a universal mechanism by which you get from these individual probabilities of being positive to the joint. And the recipe is you use the Eulerian UN. The UN of R1 up to Rn is that polynomial that comes out of the X log. And almost miraculously, exactly the same polynomial function of these different probabilities. This should be a strictly positive, I apologize. This guy should be strictly positive, gives you, this is a strict meander. And there's another very interesting one. We're talking about returns. This is the probability of a return through through non-negative values. And that, maybe I have a mistake. No, that looks correct. Yeah. Anyway, so I find it sort of slightly mind-boggling that these probabilities are related. These probability relations occur according to exactly the same polynomials up to rather trivial factorial factors as the ones that appear in the moment cumulant identity. And I basically can't think about the two things at the same time and have a sort of a coherent picture. So that's why I call it the Eulerian elephant, right? We're now we're looking at the trunk of the elephant, and before we were looking at the tail or the wall. Some different aspect of this exponential transformation. Okay, so this is enhanced. This discussion is enhanced further by thinking about permutations, and a very nice lead into that is what I call discrete uniform stick breaking, which is you have a stick composed of n discrete segments. You pick a segment uniformly, break at its right end, and keep the left. So here's my stick. It's got 8 segments. I pick a number at random. It was 3, and I break to the right of 3. And now this is my remaining stick. I break to the right of 7. I picked 7, and now the only place I can break is at the end. I end up getting 3 sticks of length 3, 4, and 1, and that is a random discrete stick breaking scheme. And the probability that I get the sequence of sticks 3, 4, and 1, it is by definition of the scheme, an 1/8 times a 5th times a 1/1, which is 1/40th. And of course, we can write down that probability for any particular sequence of stick lengths. So now I invite you to, for each stick of length j, keep it with probability r sub j independently. So the rj are now some parameters between 0 and 1, like they were in the previous slide. In the previous slide, the arguments that we fed to the Eulerian polynomials were numbers between 0 and 1. They were probabilities. So do that, and then what happens is that the probability of retaining all sticks is the un, the Eulerian polynomial function of these variables r1 up to n, rn. And the proof is almost trivial, and really trivial compared to most of the previous discussion. Namely, you just condition on the length of the first stick, right? The length of the first stick is uniform. And if you've started by choosing a stick of length j, you're going to keep that stick with probability rj, and then you're going to keep all the remaining sticks with probability un minus j. So this is a sort of an undergraduate exercise in conditioning, and recursion is to see that if you use this discrete stick breaking scheme and you have numbers r that are probabilities, then you're going to solve this recursion, and hence, of course, you have the x-blog relation. So briefly, some terminology. Most of you will be familiar with this: permutations, partitions, and compositions. Everyone knows what a permutation is. I've written it in Cauchy cycle notation. This is 1 maps to 2, maps to 4, maps back to 1, 3 to 5 to 6 to 7, back to 1, and so on. The cycles induce a partition into sets, and here's the sets induced by those cycles. A composition of n is some positive integers with some n, and we get such a composition 3, 4, 1 from this scheme. We have a partition of n is ranking, and partitions are conveniently encoded by the number of parts of different sizes. So I use an m dot for that. If we have this partition with decreasing sizes 4, 4, 3, 2, 2, 2, 1, 1, 1, that has 3 parts of size 1, 1 of size 2, 2 of size 3, dot, dot, dot. There's a very famous enumeration, which was due to Jacobi and Cauchy in the 1840s, that if you have any partition of n, you can write down how many permutations there are with a given number of cycles of particular sizes. And it looks awfully like the formula for n choose k, and basically the derivation of it is combinatorially just like the derivation of the formula for n choose k. It's a sort of double counting argument that most people will be familiar with. And the main point is there's a simple explicit formula for the number of permutations which map to a given partition. Now, this circle of ideas gives you a whole suite of summation formulas for un, the coefficient in the exponential that comes from the R1. So here is more or less the Eulerian definition that un of R1 to Rn, it's going to be the coefficient of x to the n in this beginning of an exponential sum. Now, the most elementary way to handle that is to do a sum over compositions of n. So here's a sum over compositions of n into k parts, and you just extract what you see you just extract what you see in these powers. And then you realize that all of the compositions that map to the same partition, they're all going to give you the same thing. The only kinds of thing that you can see are rj over j to some power, and you're going to have always going to have an mj factorial in the denominator, and that's just some it's just some elementary counting of how many compositions map to a given partition. So this is a sum over compositions of n. This is a sum over partitions of n. Finally, we have a sum over permutations of n. And this is the sum over all permutations of rj. Kj of omega is the number of cycles of omega of size j. And so we have this formula, which is now more or less the Polya's cycle index formula for un of R1 up to Rn. This polynomial in probabilistic terms is the expected product over cycles of a uniform random permutation of weight factors rj, one weight factor rj for each cycle of length j. And then also in probabilistic terms, this is just a joint probability generating function of the sizes of different cycles. Okay, so I should try, I'm just going to be very sketchy in the last few slides. I wanted to talk briefly about concave majorants, and I'm showing you here a construction that goes back, some elements of it go back to Spar-Anderson. This is detailed in a paper with Josh Abramson around 2010, and we did some refinements with Nathan Roths and Geronimo for Levy processes. And just recently, Alex Mijatovic and some co-authors have a number of refinements. So this whole business of analysis of concave majorants of processes is very much thriving with new ideas coming in. So I just want to explain the idea that the main idea from the work with Josh Abramson. So here's a model. We have a random walk. Let me say the first thing. The first thing is we do a stick breaking split of 1 to n. So we have a time index. We've done a stick breaking split like in the previous slide. The stick breaking produced 3 segments, let's say. Now, on each segment, you run the random walk starting at 0, and it gets where it gets. And then you restart on the next step. You run it, and it gets where it gets, and you do a final segment. So if your stick breaking produced 3 sticks, you run 3 random walks independently for the lengths of those sticks. Now, you see I've joined the beginning and the end with a line, and I've drawn a parallel line, which is the touching point of a line of the same slope. And what I do next is I say I'm going to put these segments in the order of slopes of these lines. So this, let's see, this segment is going to come first. It's going to come here. So this sloping line is exactly the same slope and length as this line. The second segment goes here. That's come from here. The third segment is the first thing. So we've rearranged the slopes so that they're now in segments of slopes of decreasing order. And we've done one more thing. We have done a Vervat style transformation, which is we have started each walk at its argmax relative to this slope. And so I'm using this as the starting point. I'm going down, and then finishing with this, down, and then finishing with that. So this is a path transformation, which gets you from a stick breaking scheme and a bunch of independent random walks to a new path, which has its concave majorant, built along with the path in a very easy to comprehend way. And essentially the theorem from Abramson and myself in 2010 is that this scheme creates a copy of the random walk run for n steps jointly with its concave majorant. And that assertion is entirely consistent with the X log discussion around the fluctuation theory. In fact, it's sort of that discussion is somehow built into it. Just 2 or 3 more slides. On another theme, one of my shared interests with Jean has been variations around reflecting in the maximum. We had most of the discussion in discrete time. Let's do it in continuous time. You have a Brownian motion, BT. It has a running maximum, MT. And if you reflect the path at the level of the maximum, you get a new path, 2MT minus BT. And if you just subtract the two things, you get an MT minus BT. So by now well-known results. Lévy showed that M minus B is a one-dimensional Bessel process. I showed in 1974 that the 2M minus B is a three-dimensional Bessel process, better understood as Brownian motion conditioned to be positive. And that's, as I say, it's a theme that's been picked up by Lévy processes, or for Lévy processes by Bertoin, Doni, and others. There's an extensive discussion of these things. I want to do something which I just do by force of habit that I find interesting. Suppose we take a Brownian motion again. Now look at its least concave majorant. So the least concave majorant is K, and I can do the same thing. I can reflect the path in the concave majorant, and I get a path which I can call 2KT minus BT. Now, Grönboom showed that if you look at K minus B, you get a succession of independent Brownian excursions whose lengths are driven by the dynamics of K, somewhat complicated, but describable. Recently, where there's an archive posting this year, Mehdi Ouaki and I have shown that the one-dimensional distributions of 2KT minus BT are precisely those of Bessel 5, and that's true for each T positive. And we were very struck by this and wondered, of course, could it be that 2K minus B is actually a 5-dimensional Bessel process? And I'm a little embarrassed to say that we cannot resolve that. And so we're even struggling to describe the 2-dimensional distributions, and we do not know whether it's Markov or not. So as a, I think, fairly difficult open problem that should challenge members of this audience, take a look at our paper and see if you can settle for us whether or not 2K minus B really is Bessel 5. It looks like it in many, many ways, but is it really a Bessel 5? Perhaps I should stop. I do have another problem with Poisson crossings, but I'm running over time, so I should stop. I want to thank Jean for all his inspiration over many, many years, and wish him a happy birthday and many happy returns of the day. Thank you.
Thank you, Jim. So are there questions or comments in the audience?
So hi, Jim, and thank you for your very stimulating talk. I think, okay, it's an old result that you presented, this construction of the concave measurement, but it's very striking. And I was wondering, did you try to work with other partition than the uniform stick breaking scheme? I mean, you've done a lot on Poisson-Dirichlet partitions. I mean, if I'm looking at the continuous world, what would you get if you take a different stick breaking scheme, not using the uniform one at each time, but and construct? So you will get also a concave measurement of something. What would be the something?
Well, the answer is I don't know. I think you will get a mess. You are right to point out that there is an analog of discrete stick breaking, which is basically the discrete analog of beta stick breaking, right? In the continuous world, you can construct the so-called GEM process from stick breaking with IID betas. There is an exact discrete one where you're essentially using beta binomials instead of betas to break the discrete sticks. So there are many results which have analogs with a parameter theta in them, not just the uniform case, but I am not aware of any such analog that has to do with random walks. Somehow the connection between the dynamics of the walk and the partition, it's maybe brittle is the word. I mean, it's very fine. It just sort of works magically. And I don't know, I did describe to you today many of the components which somehow make it work. But unless you have all of these components together, it doesn't work so magically, as far as I understand. And so that's a very interesting question, but I don't know any interesting generalizations of that with other partitions.
Okay.
It would, yeah, something to think about. And I did not think about it seriously, but I'm guessing it's tough.
So other questions, maybe in the chat or Julien?
Just a little question about your open problem. Do you have supporting simulations for multi-point distribution for this convergence to the SL5, or just one-point computation?
Oh, okay. So there is an issue with simulations. I don't think you can tell the difference at the level of simulations. So certainly we have done some simulations, but they're somewhat inconclusive, I would say. Let me say where, for the 2K minus B problem, let me say where the real difficulty lies for 2 dimensions. There is no a priori limit on the number of vertices which might be between times S and T. You know it's finite with probability 1. I'm not sure we have even a decent formula for its distribution. It is, it's some multiple integral, but it becomes a higher and higher dimensional multiple integral, and the integrands are very difficult. So it's even somewhat annoying to simulate multiple multiple segments, though it can be done.
To simulate exactly, you cannot. Right? You can just do approximation, and you don't know how accurate they are.
I think you can simulate exactly, and I think so. There's a paper of Carolyn and Dijkstra, which we should cite in the preprint. And that basically it's it's a stick breaking type scheme, right? You make a segment and you make another segment, but the issue is you have to make enough segments to be sure you've crossed between S and T, right? And so you are always going to have some tail in your distribution for, well, have we, we've gone out to 10 segments. What about 20 segments? That's.
Thanks.
If I may ask another question, I mean, bouncing on what Nicolas just said. So the Pitman 2m minus x theorem holds in the discrete setting for the simple random walk. So maybe you can try at least for a random walk with 2 steps, 3 steps. To see.
So my impression is that there is no obvious discrete analog of the formula of the result. It doesn't seem a very natural. You see right away the problem with the definition of the excursions, right? I mean, they're just discrete random walk is very difficult for study of the concave majorant because the discretization is really annoying. You have so if you look at the construction with Abramson, you can make you may get segments of the same slope multiple times, and that makes things difficult. That means that it means that the stick breaking process is not actually embedded in the concave majorant. It involves extra randomization. So the whole discussion of concave majorants is complicated in, strangely, what appears to be the simplest case of a coin tossing walk. You might be better off dealing with a Laplace walk, two-tailed exponential or something like that. That's more likely to have exact things which might work out nicely. So certainly looking for some discrete analog is a reasonable thing to try and do, but I don't think the most obvious one works.
Can I ask a question? Hello?
Yes, yeah, well, that's Takis.
Yes, hi. Thanks for the talk. It made me want to ask 100 questions, but I'll only ask one. It's almost similar to the one I tried to ask Steve Evans the other day. This old paper of Spitzer, where he talks about Wiener-Hopf factorization and so on, he used a correspondence between the 2 representations of permutations with cycles, as you said, and ordinary representation. And that leads to something that later was called Bohnenblust-Spitzer algorithm. Steele calls it like that, Michael Steele. I was wondering, in all these things that you mentioned, whether this comes up or anybody has explored this further, if you know.
Okay.
Yeah.
So I'm certainly. The discussion, I gave a limited discussion where I just derived the part of the Wiener-Hopf that only involves the times. There's another part that involves the levels. I have a paper with Cindy Greenwood from the 80s where you know this paper, right?
Yes, of course, yes. So one
of the interesting things is in that paper, we entirely work with ladder indices, and it's just using the fact that the geometric distribution is infinitely divisible. So it's exploiting this kind of infinite divisibility discussion that I made today, and the fact that we understand in that setting, we understand the x to the n over n as coming from the Levy measure of the geometric. Now, in that discussion, we did not look at concave majorants at all, and that's a different perspective on the fluctuation theory, is to frame it in terms of concave majorants. To be honest, I forget exactly what the Bohnenblust-Spitzer algorithm is. It's a good point. I should go back and try and include that. I'm attempting to sort of collect together a kind of a revised view of these old favorite things, And I've certainly looked at the Spitzer work, but I did not. You remind me about Bonenblust, which I've forgotten.
Okay, I actually thought that this was your motivation when you were writing the papers on convex majorants and so on, because it's just something. There's some questions there waiting to be asked, I feel.
Yeah, well, I'm sure there are more questions around. Yeah, more questions around and more, connections to be made.
Mm-hmm. There's a little
there are still more sides of the elephant.
Yeah, yes. Thank you.
Other questions? So if not, let's thank the three speakers of this afternoon.